Okay. So, so what do you usually do in your just I'm happy to give a talk. I'm also happy to be very informal and to have you ask questions at any point. And I'm happy to just talk about other things too. So whatever you want, like um, career questions and broader questions about research, everything's game. Um, does that work for you?
Yeah, that's
Um,
perfect.
and I have this set up so that I can see some of you on the side. Let's see. I can see many of you, but not all of you. So if you want to say something, just speak up. Um, okay. So I didn't know what to talk about of all the different things that we do in my lab, so thought I'd kind of give you some general ideas about how we've been thinking about learning. That comes out of a lot of research that we've done in the last 10 years. Um, and um, the main idea that this starts from is the fact that no two events are ever the same, right? How do they say it? You can't step into the same river twice. You can't take the same semester twice. Can't go to two classes that will be the same. Um, so if we're thinking about learning, learning is about taking experience from one situation and applying it to another situation. So kind of at the root of that has to be something that I'm going to call generalization. Basically, if because no two events are exactly the same, I have to generalize and say these two events are similar enough to each other that I'm going to say whatever I experienced last time I went to that restaurant, now I'm at this restaurant again, but lots of things might be different. For all I know, the chef might be on, might have changed, or this is their off day. A lot of things are different, but I'm going to take that old experience and say whatever I liked that time is probably similar this time, and I'm going to learn from that previous instance to this instance. And any kind of learning that you can think of involves this kind of generalization. One of the examples that I like to think about most is just a simple task like crossing the street, right? So if we have any learning from experience, like you can learn over time that, in Manhattan, you can jaywalk. In Princeton, you can, but the cars will stop as if like, they will stop from afar and be like, whoa. In Washington, D.C., you can get a ticket for jaywalking. So you learn from experience, even though you kind of know how to cross the street. Your parents maybe taught you when you were young, but there's still more learning from experience. But you don't want to just, you want to generalize and say, what I learned from this street crossing, I'll generalize to other situations that are similar enough. So then that raises the question, what is similar enough? Where do we set the boundaries? Because I do want to learn differently about crossing the street in London, where the cars come from the other side, or even in Manhattan. Than in Manhattan, you can jaywalk on a 4-lane street, and that's okay. Don't do that on Route 1, right? So you do want to set boundaries on generalization. So from many years of studying learning, I've moved from thinking about how do we learn from an experience to what do we apply that learning to? How do I decide what is kind of what is the category of things that I'm learning about right now? And you might think that this is relevant to difficult real life learning in humans, but also if we think about animal learning, it's not really obvious where they set boundaries and why they set boundaries between what they generalize from one situation to another. And I want to start by showing you how many of you, do any of you work with, do any lab work with animals, with rats? I see Yoni, right? That's your name? Uh, Maybe, okay, so a few of you. So I'm going to show you a little video of rat fear conditioning. So what you see here, the first phase is the rats are pressing a lever and eating food happily, and a tone is going to come on. Oh, I didn't do optimize for video. Can you see this okay? Yeah, okay, so when this light is on, that's when the tone is on. There's no sound in this video. And this is just to habituate them to the tone so that they're not afraid of the tone on its own. And now on the next day, they're undergoing conditioning. And conditioning, the tone is on, and at the end of the tone, they're gonna get a little foot shock. You'll see them jump a little bit. That's what happened with the foot shock. And now the test 24 hours later, so one pairing of a tone and foot shock is enough to generate learning in animals. So now the tone is on and you can see their response. You can see that they are freezing. That's the fear response in rats. You can see that the timer is still on. So it's still going. So, and this guy is like moving against all odds, trying to get to the food without the predator seeing him. So that's a really basic kind of learning, very fast learning in that's studied a lot in rodents because it is a model for a very, very strong fear memory, like post-traumatic stress disorder. So very fast learning, one-shot learning that totally changes rats' behaviors. Rats in kind of their normal behavior, they don't freeze. They're more like fast forward animals. They're moving and doing stuff all the time. We just got 2 mice as pets actually yesterday. And my son is so excited. And oh my God, they're so fast forward. Like they really do not stop for a second. But I know that if you condition them with fear conditioning, they will freeze really well. So it like completely changes their behavior. So the question is, okay, so we have this simple conditioning. We paired an acquisition, we paired a tone with a shock. And now we want to undo that memory, because if that memory is like, or that association is like a situation of post-traumatic stress disorder, one question is, how can we cure that? How can we make the rat not afraid of the tone anymore? So do you have any ideas of what you might do?
Chocolate when the tone goes on.
Say again?
Maybe give chocolate to the rat when the tone goes on.
Okay, so what you're suggesting is called counter conditioning. So you can condition the tone now with something positive, appetitive, like chocolate. I mean, rats don't love chocolate. You know, you can give them their favorite food, not chocolate. Other ideas?
As opposed to giving them something, you can just play the tone and have nothing happen, just so that they can normalize the tone and break that association between the shock and the tone.
Yeah. So that's what people do a lot in many experiments. It's called extinction. So the idea is we now play the tone with no shock over and over and over again, maybe 30 times, 25 times, until the rat realizes that this tone doesn't cause shocks.
What if you played a different tone
You
and
could play
associate that tone with the shock?
like it takes over. That is an interesting idea. It actually might do the opposite, because this kind of learning is very resistant to just forgetting. So now they'll be like, ooh, tone 1 causes a shock and tone 2 causes a shock. Maybe every tone causes a shock. Like it will just enhance generalization of fear from tones in this scenario. But the counter conditioning idea of giving something appetitive, not just extinction, but giving something appetitive, that works. And there are some studies that suggest that that might be better than extinction, or make extinction faster in some sense. But the problem is with this, so it works. If you do extinction, if you play the tone with no shock, over time, the rat freezes less and less. Actually, almost never like zero freezing. They go down to like 20% of the time they're freezing, 10%. They're pretty fearful still, given that they've once had a shock. But that's not the problem. The main problem is that this extinction learning seems to be pretty fragile. So if you wait a month and then put the rat back in the box and play the tone, you'll see that they're freezing again. So somehow there's spontaneous recovery of the association between the tone and the shock over time. or if you test the animal, you don't want to wait a month. That's too long when you're, hurrying to do your experiment. But you can test the animal even the next day in a different box with the same tone, and they'll freeze more. So that's called renewal. So renewal of fear. Their fear renews in a different context. And if you think of this with respect to PTSD, it's quite bad, because in PTSD, let's say someone who has post-traumatic stress disorder, they're very fearful of things that are pretty benign, like this tone, right? So they were in one very bad situation. Let's say they were in a car accident, and now they're afraid of every car. They won't get into a car. They don't want to drive anywhere. They have a really hard time going to visit their family who's far away, because they don't want to get into a car again. So you might do some desensitization of cars and of a car and an accident in some way, like by talking about it in the therapist's office. But then if it doesn't generalize across locations, if this rat is just not afraid in this box, but you put them in a different box and they're afraid of the tone, that's like this person then leaving the office of the psychologist, and it did not help in real life, because in a different context, they'll still be afraid of cars. And the last thing that I want to, so the third way to show that extinction is fragile and that fear memory is alive and well, is if you just give the rat a reminder shock with no tone, just like, remember that shock, and then test them. And you see here that I just brought one of like many studies that show this. All these phenomena have been shown many times. So this is called reinstatement of fear. And here is with no reminder shock. You see that the rat freezes only like, 15% of the time, but with a reminder shock, they're now freezing like 45% of the time when they're tested with a tone alone. So it seems like extinction is not unlearning of the old association, it's something else. And people have interpreted this as, in extinction, what happens is the rat learns a new association, tone, no shock. It doesn't erase the old association of tone, shock. It just competes with it. And this new association, for some reason, is weaker than the old association. So the old association can then like kind of spontaneously come back over time. And so this for us was quite puzzling, because we were like, we want a theoretical explanation for why that happens. When does the rat decide to start a new association versus learn the old association? This is already like leading us to boundaries of generalization. Like, why not in the middle of extinction start a new association? Like, why in the beginning of extinction? Why not, between two trials of acquisition? What is the theoretical explanation here? And the way we think about it brings me back to the cartoon that I had in the very beginning, which is to kind of rethink, what is the animal actually learning? And this was work by Sam Gershman, who was a graduate student in my lab. He was actually he was like the first cohort of graduate students in my lab when I just started my lab. He's now faculty at Harvard. And he thought, when we're thinking of animals learning that a tone causes a shock, this is one thing that they could be learning, but it would be incorrect, right? Because the tone didn't cause the shock. What happened was there was some hidden cause, some latent variable. In fact, that was the experimenter who caused both the shock and the tone. So this is a truer depiction of the causal structure in the world. So maybe we need to think about rats being kind of smarter than just associating between observable events. Maybe they're also inferring some unobservable causal events and associating them to what they observe. And when you think about that in our daily life, we constantly assume for different events that there is something hidden from sight, gravity we've never seen, and all kinds of other things that is the cause of things that we see. This is not far-fetched to think that we learn causal structures, and we don't just assume that all the causality is between things that we observe. But now once we say, okay, an animal can infer a hidden cause, well, they might infer 2 hidden causes, they might infer 200 hidden causes, that there's kind of no limit on how complicated the causal model of the world that they might learn. And so what we want to do is kind of in that, well, we as humans like simple explanations, like parsimonious explanations of phenomena. We're assuming that animals like that as well. So what we wanted to do is model animal learning, assuming that animals prefer a simpler model of the environment, but they want to learn a model that actually explains the observations that they see. So what we're going to do is use this framework, a framework of Bayesian inference. So in Bayesian inference, the idea is the animal, and an animal can be, a rat or a human, we're all animals. The animal has some assumption about how the world usually works. That's called the prior, or the generative process, how I assume that things are generated in the world. And given that generative process, and given the things that I see, I can infer what were the actual causes. So the generative process that we're talking about, or the generative model that we think animals have in their head, we want to give them a generative model that is flexible enough to capture the actual structure of the environment, but constrained enough to allow some generalization, some learning. Not, if there's a different latent cause for every event that we see, then we can't generalize at all, because what do we know what's going to happen next? It's going to be a completely new latent cause. So the way this works is this. This is a model called a Chinese restaurant process prior. I didn't invent that name. Apparently people in Stanford invented it who really like to go to Chinese restaurants for lunch. They also have an Indian buffet process. That's a different model. And in this model, the assumptions are that each trial, or each set of observable events, is caused by a single latent cause. So that starts by being simple. And another thing that keeps the model small and simple is to say that all else equal, a recently prolific latent cause, so a latent cause that's caused a lot of observations, a lot of previous trials, is more likely to cause another trial. So rather than assuming a new latent cause on every trial, I'll say, whatever has been active recently is probably going to be active like in the next instance. Let me just go through the end of it, and then I'll go through the math for those of you who come from a math background and prefer that. But then we want it to be flexible enough to really account for the structure of the environment. And that part of the third part of the model is that allows that, says that the number of possible latent causes is unbounded. So you can always, there's always some small probability for a new latent cause. And that's what you see in this equation here. This is really just if this makes more sense to you than these words. But the idea here is that the probability that the latent cause C of trial T is cause number K is proportional to NK, which is the number of trials that have already been generated by cause K. That's if K is an old cluster, or with some small probability alpha, there's a possibility for a new cluster, for like a new K. So if you think about it, like trial number one is caused by cluster and cause here are the same. Trial number one is caused by cause number one, and then trial number two will have some probability of coming from that same cause and some probability of coming from a new latent cause, cause number two. And then trial number three will have some probability of coming from latent cause one, some from latent cause two, and some from a new latent cause. And so the probabilities of new latent causes here get smaller and smaller over time because alpha is fixed and T, the number of trials, just grows and grows. And clusters or causes that have already been assigned a whole bunch of trials are more likely to cause the next trial. And so this is the prior. The one piece that I haven't told you is how do we know whether to assign a trial to latent cause 1 or 2 or 3 or 5. And that comes from the likelihood from basically assuming that each latent cause tends to produce similar trials. So if latent cause number 1 caused a tone and a shock, and I again see a tone and a shock, it's more likely to be that same latent cause. But if I see a tone and no shock, or a shock and no tone, or something completely different, chocolate falling from the sky, probably a new latent cause, because it's very different. So that's how the model works, and it's called Chinese restaurant process. The analogy is if you think of each table as being a latent cause, and each customer coming into the restaurant as a trial, and customers prefer to sit at tables that already have lots of customers in them, and then they eat some characteristic dish, like each table has its own dish that they're eating. This is a Chinese restaurant, so family style. But once in a while, you start a new table, and that, you know, that can happen too. Questions? All good? Okay. So the idea here is that in an extinction task, the true causal structure is, so I said that you can train animals with one tone shock pairing. That is true, but usually, just to be sure, people do it, have 3 trials in training. So in training, there's one latent cause that causes these 3 trials with tone and shock. And then in extinction, there literally is a new latent cause, right? We changed the computer program so that now shocks are not given, and now we have a whole bunch of trials with tone and no shock. And this is the true generative process that generated the observations. But the rat sees only the observations and has to infer somehow what was the latent structure. And the idea here is that using the prior that I just gave you and kind of enumerating all the possibilities and asking, you know, it could be one latent cause that caused everything. It could be a different latent cause for each trial. It could be any combination in between them. This combination that I'm showing you here will be highest probability because the trials that are generated by each latent cause are very similar, and they're, you know, these latent causes are pretty prolific, and, you know, the prior kind of gives this high probability. So that's how the inference works. And so when we think about reinstatement, what happens in reinstatement? We give a shock, and that would suggest to the animal that, wait, this latent cause is now active again. And maybe then it's no wonder that on the next trial, they're freezing, because they're freezing more because they're like, oh, this guy is back in town. It's quite likely that on the next trial, that tone will be followed by a shock. Questions?
I have a quick question. So
Yeah.
if you're allowed an unbounded number of latent causes, when the mouse experiences a shock with no tone, why wouldn't it attribute that to like a new kind of, like there's a new context now where I get shocked with no tone? Why wouldn't I give it, like attribute that to a new, like a totally new cluster?
That's a really great question. And they actually do. I mean, I don't know what they do. When we model this, our model does that as well. So it attributes this trial partly to a completely new latent cause, partly, it's all probabilistic. It's not like, you know, hard assignments, and partly to this old latent cause because this one is more prolific than the new latent cause, and because it already had shocks. So it will be both.
Okay, yeah, that makes sense.
That's a great question. So I said clusters causes the same thing because the idea really is that if we think about our daily life, you know, our daily life is not divided into trials like, you know, here's the stimulus, here's the outcome, please learn the association. It's more like we hang around in the world, bits of experience impinge on us all the time. And the first thing that we have to do is decide, you know, what goes with what. And so we cluster these experiences based on what we think their latent causes are, like all the things that we think are caused by the same thing, because they're similar, we cluster them together, and then what we learn about one affects what we think about the other. So that's kind of the boundary of generalization. So if the rat clusters all of these extinction trials together and all of these acquisition trials together in 2 different latent causes, then what they learn about these trials will be separated from what they learn about these trials. So that's the idea, that if all of learning is generalization, latent cause inference, or inferring the current cause, or in reinforcement learning, it's called the current state of the task, sets the boundaries of generalization. And what I want to do in the next like 15 minutes is show you 3 experiments where, so we came up with this theory and then we wanted to test it, to test kind of the qualitative predictions of this theory, to convince ourselves that this is really maybe somewhat true. And these are experiments, these are all behavioral experiments, 2 of them in humans, 1 in rats. So the first experiment that we did was to test whether similarity really determines the boundaries of generalization. Like similar things will be in one cluster and different things will be in 2 different clusters. And so learning about one won't generalize to the other. And to do that, we gave subjects this task. We showed them a lot of circles and said, guess within 3 seconds, they had to like type like a double-digit number. How many circles do you see? So how many circles do you see? Throw out numbers. You have to do it within like 3 seconds. There's not time to count. Just guess. Ah, you're writing in the chat. Let me see. Okay. Okay. I see 32, 29, 25, 41, etc. So the subject would guess their number, and then we would tell them how many. 39. Did anybody get it? 38 was pretty close. 40 was close. Nobody got it exactly. Cool. Okay, here's another trial. How many circles? Oh, I have another few that are only 1 off. So the number is 61. So that's how the experiment went. So literally trial by trial, they would guess and we'd show them the actual number. And we weren't interested in people's fast counting abilities. We were interested in how they learn from the true number that we give them, what to guess on the next trial. Because the number of circles was drawn from a Gaussian with some mean. So over time, you're getting information about the mean of the Gaussian, and you can kind of learn from that what to guess. But there was one trick, or one thing that we didn't tell subjects. So trials came in 2 flavors. As you saw, there was one trial where all the circles were red, and another trial where all the circles were yellow. So that was true in the experiment as well, but we never mentioned color. We just said, your task is to tell us as accurately as possible how many circles you see. In reality, the Gaussians, the means of the Gaussians from which the number of circles were drawn were different for the 2 different colors. So here, the mean for the yellow circles is 65, and the mean for the red circles is 35. And indeed, you saw there were a lot fewer red circles than yellow circles, although there's overlap here. There would be trials where both of the, there are some trials where the yellow circles are about 50, and there are some trials where red circles are about 50. So these are not extremely different distributions. So that was in one type of block. So people did this experiment in blocks. The blocks were not signal. We didn't say, end of block 1, beginning of block 2, but each block had 2 different colors. So people could notice that something changed, or they could just ignore color, whatever they wanted. But the blocks came from either condition 1 or condition 2 randomly interleaved. And in condition 2, one of the colors that I'll call yellow here just for illustration purposes, but one of the colors was still mean 65. So there's always one color that's mean 65, but here the other color is mean 55. And so our hypothesis was that in condition 2 trials, people would basically, because these 2 colors lead to similar numbers of circles, they would basically ignore color and learn the overall mean, which in this case is 60, and start guessing close to 60. Whereas in condition 1, because these are different, they wouldn't ignore color. They would learn 2 different distributions. And so when we ask them about yellow circles, so what we're going to do is compare only their guesses on yellow trials, because yellow trials are identical in these 2 conditions. And I'm guessing that in condition 2 in yellow trials, they'll guess closer to 60, because that's the overall mean. And in condition 1, because they separated them into 2 different causes or 2 different clusters, they'll guess closer to 65, because they're kind of not being contaminated by the red trials. Does that make sense? So of course, I wouldn't tell you this if that's not what we got. And we got it in multiple experiments. So this is totally, this is not hard to replicate. So you see here that in condition 1, they are guessing closer to 65. And in condition 2, they're guessing closer to 60. And this difference is small but significant and replicable. And I personally really love, I think like of all the experiments, very fancy stuff that we've done in the lab, I love this experiment most. It's really, really simple. In fact, we put it together in like a week because we had some deadline. We needed preliminary data for a grant. And it's, if you ask subjects, they're not aware, they won't tell you, I know I noticed here differences, that it could be that this process is completely implicit. I once gave a talk about this, and someone raised her hand from the end of the auditorium and said, I was actually a subject in that experiment, and until you talked about it now, I didn't even notice that there were colors. Right? We didn't say anything about colors, but the thing is, the colors are very obvious. You can't miss them. But if you take them into account all the time and learn separately about each color, then there shouldn't be any difference between the yellow trials here and the yellow trials here. And if you consistently ignore color because we didn't say anything about color, then obviously you'd be less accurate in condition 1 because the overall mean here is 50, but they were more accurate in condition 1. So from that pattern of results, the only way that I can explain it is that in condition 1, they decided to not ignore color, and in condition 2, they decided to ignore color. So they were basically inferring whether there's one latent cause that causes everything or two latent causes that cause it two different colors, and they were learning based on that. They were generalizing based on that. Questions?
Just a quick question for
Mhm.
clarification. What determined condition 1 and condition 2 again?
It was just random, they were doing different blocks, maybe like 20 blocks per subject, and 10 of the blocks were condition 1, 10 were condition 2. They were randomly interleaved. So there was nothing to signal to the subject what condition they're in.
Oh, okay, thanks.
And I see here that this is the wrong citation. We have this is a citation for the Chinese restaurant process model paper, but it took us many years, but we finally did publish this. It was really hard to publish because it's like this simple behavioral experiment, and we're so gung-ho about it, but people are like, what? That's not much. But I love it. So that was experiment 1. But then I said here specifically that we cluster experiences together into memory traces based on similarity. So we had a hunch that this separation into what we generalize over and learn learn together about is also how we maybe organize our memory. Like we literally put all the memories of all these trials together in one area, and that's why we can generalize across them easily, and in fact they might interfere with each other, and we put these somewhere else. So to show that, we ran another experiment on humans. This was Sam the same Sam from before, and also Angela Radulescu, who was then a new research assistant in the lab and now is also finished, graduated, and now faculty at NYU. So this was also quite a long time ago. And what they did was this. They had human subjects look at little line segments, and each line had a length and an angle, an orientation. And we wanted them to really pay attention to these lines, so we made them try to predict the next line. So here they're predicting the next line, so they're taking a mouse and literally drawing where they think the next line will be. And then they see the next line, and the closer they were, the more points they get. Sorry, so this is their prediction, and here's the line, and they earned 60 points because they were quite close. And down here you can see this shows trials. So this moves trial by trial. So here's the next trial, predict the next line. They're predicting it, getting 80 points this time. And what we really wanted them to do is, as I said, pay attention to the line segments that we're drawing that change from trial to trial, because at the very end of the experiment, so let's do the last trial here, please predict the next line. They are predicting, getting 85 points. At the very end of the block, not the end of the experiment, they did a whole bunch of blocks of this. This is a pretty boring experiment. We asked them to reconstruct from memory one of the first lines that they saw. So the first, second, or third line. And here, like in the circles task, we had two conditions behind the scenes, or two types of blocks. One block I'm going to call the gradual block. And so what I'm plotting here is each trial, what is the length of the line that is the true line that they're trying to predict, and what is the angle, the orientation of that line. And you can see that it's this kind of small random walk with small changes, plus minus, I don't know, like 3 in length, and plus minus some of the like the same in angle, just making sure that we don't backtrack. So this is gradual change of the line. It's always changing very gradually, versus another type of block. So there were half the blocks were gradual and half the blocks were of this kind, a jump block, which is identical, except that in the middle of the block, there is one change that's a lot bigger. There's a jump that's 4 times the size of our usual changes. So now the line is becoming quite a bit longer and changing angle quite a bit in one trial. And our hypothesis was, if this is true about memory traces, then here in the gradual blocks, all of these trials are so similar to each other that they should all be kind of stored in the same memory trace. So they would basically all interfere with each other. Whereas in the jump condition, maybe the jump would kind of start a new memory trace, because this is like, you know, these were the short lines that were kind of north, northwest, and these are the long lines that are more like south. And so as they're experiencing these lines, they're not interfering with these initial lines. And so when we ask them to recreate one of the first lines from memory, they should be better in the jump condition that had less interference than in the gradual condition. And we controlled for the distance between the end and the beginning. So it's not that here they're farther or closer than here. So then we ask them to generate a line from memory. This is a hard task. They're not very good at it, but you know, maybe they generate a line that has this length and this orientation. And now I can measure how far that line is from what I'm asking them to actually remember. So the shorter the distance, the more accurate they are. And I can also measure how far is that line from the very recent trial. So right, this was right after the end of the block. And the larger that distance, the better, because they're less influenced by what they just saw. And so here are the results. So you can see that in the jump condition, indeed, the distances to the start were smaller, so they were more accurate, and distances to the end point were larger. I mean, these are, again, small effects, but significant. This is, as I said, a hard and boring task. And we can also model this task with our model, and indeed, it infers 2 latent causes here and 1 latent cause here, but that's maybe not surprising. We kind of, you know, generated the task so that it would, that would apply. So in general, this led me to think, so kind of the autobiographical tidbit here is, when I went to college, I really wanted to study the brain. Like you guys, I was really interested in cognitive psychology, cognitive neuroscience. I was especially interested in memory because I have terrible memory and I wanted to learn how to fix it. I wanted to, like, the big research question in my mind is, are there different memory styles, and can you change yours to a better one if whatever you have doesn't work? And I didn't end up studying that. I mean, I took a class on memory. It was the very first class that I took. I was very excited about that, but somehow I kind of drifted to learning and ended up doing my independent work on reinforcement learning, and kind of stayed a reinforcement learning researcher to this very day. And I used to think, you know, that's not a problem because learning and memory are really the same thing. Everything that we have in memory, we had to learn, and everything that we learn, we have to like put in memory. So it's really just 2 sides of the same coin. But now I actually think about it quite differently. I think, like, yes, 2 sides, 2 opposites of the coin, because it's kind of either or, in the sense that if you think of this latent cause process, so, you know, trial number 1 comes in, trial number 2 comes in, trial number 3 comes in, they're all similar, they're all in 1 latent cause and 1 memory trace. And then comes the outlier, right? The first extinction trial. And now that's where the battle between learning and memory comes into play, because if you think about this in a learning perspective, reinforcement learning, Riskorla-Wagner, if any of you are familiar with that model, then the idea is, I just learned that, okay, before I thought that reinforcement was 100%, now I know that it's actually 75% reinforcement. I've basically updated my association between, and the shock is reinforcement because reinforcement doesn't have to be appetitive, it can also be aversive. But anyway, the probability of the outcome, the probability of the shock, I've updated it to 0.75. Which is basically taking an old memory that I have, which is tones cause shocks, or tones are associated 100% with shocks, and changing that memory, modifying it. Or I can do, like, if you talk to memory research people, not learning research people, they would say, well, this is different. You'll make a new kind of episodic memory of it. You're not going to go and disrupt that memory that says tones are followed by shocks. You're going to make a new memory trace that says, well, except this one. And that's, in our model, creating a new state or creating a new latent cause, a new cluster. So really, at any point in time, and we know that in our model, it's probabilistic. You can learn a little bit and memorize a little bit, but really memorizing is saying, I'm gonna write something new and not disrupt that old memory. And learning is literally going and changing an old memory. And so very different processes. So the question that comes from this, so how can we take this model, this idea, and use it to erase a fear memory? What do you think?
I think I'm not sure if it's so much the problem of the fear memory. I think the issue lies where it's you're perceiving a similar stimulus, and then you're using the same processes to kind of, or the same memory to analyze that stimulus. So it's not so much that the goal should be erasing the memory, but rather finding a way so that we take a similar stimulus and don't necessarily apply it based on that memory, right? Because no matter what, that's like a fundamental part of, I think, us, right? We're going to take what we have and we're going to apply it to something new that may or may not be similar, and how similar it is will depend on like our reaction, right? But
so yeah, this sounds a little bit eternal sunshine of the spotless mind, right? Like
yeah.
erase an old memory, right? Like, so
Yeah.
someone has undergone some trauma, then of course, they're not going to forget the trauma, but we want to kind of erase that association between something that is not inherently traumatic, like maybe someone has had a trauma in a crowded place. So now they're afraid of crowds. They never go to the mall. They never go to anywhere. So crowds are not the dangerous thing, right? They did have a trauma, and it's okay for them to remember that. But we want to disassociate this strong link between crowds and something bad happening. So there is a memory that we want to erase. It's not a memory of an event so much as it's an association that's like really hardwired, well, not hardwired, but wired strongly into their brain. And I'm seeing here comments in the chat. So Sonal is saying, I think an attempt to override it would help with more positive associations, or maybe work with smaller doses of the fearful thing. So indeed, what we were thinking is, the main problem, the reason why extinction causes new learning and not old learning is because the extinction trial goes to this, new cluster. And so it doesn't actually affect that old association. So what if we make extinction more similar to acquisition, as similar as we can, to kind of coax the animal to know, put that new trial here, rather than in a new cluster. And so that's what we did. So this is the third and last experiment that I'll show you. And this is the only experiment that we've done on rats in my lab since its inception. We sent Sam to Marie Monfils' lab at UT Austin because I don't have rats in my lab. I did do rat experiments when I was a graduate student, but I don't anymore. And what Sam did is he trained rats with the regular acquisition protocol, so 3 trials of tone and shock. So instead of drawing the tone here each time, each bar here is a stand-in for a tone. That was an acquisition. But then on extinction, which is usually the next day, and he indeed did it the next day, he gave them first a tone and a shock on the first trial, kind of like, this is similar to yesterday. And then a tone with no shock. And then another tone with a shock, and then 2 tones with no shock, and another tone with shock, and 3 tones with no shock, kind of gradually kind of weaning them off the shocks in some sense, but at any point in time kind of saying, that this is not very different from what you've seen so far. Please put all those trials in that old latent cause. And to the extent that the animal is putting all of these trials into one latent cause, then that latent cause is slowly being diluted. There are more and more trials without shocks here. So the probability of shock, the overall probability that they might learn, is getting smaller and smaller. And so the idea is that this will make that old memory, that old cluster, less fear-invoking. So we call that gradual extinction. And we compared it to another group of rats that got the regular extinction protocol. So in extinction, same number of trials of tone, no shocks at all. And because we're good psychologists and we know that you need to control for everything, we also had one more condition, another group of rats that we called gradual reverse. And here we're giving them 5 shocks in extinction, but in kind of the opposite order. So things are getting worse rather than things are getting better. So we start with 1 shock, but then we're like, you think that it's like yesterday, but no, this is like very different. And we're hoping that here, this will be enough to create a new latent cause. And then all the new stuff will kind of fall into that new latent cause. Or maybe the shocks will fall into the old latent cause and all the no shock will fall into the new latent cause, which is still fine, because as long as the no shock trials are not falling into the old latent cause, this should not work. At the end of all of for all the groups, at the end they had 9 trials with no shock, so that their freezing would be reduced. And indeed, all 3 groups of rats froze to the same extent, kind of between 20 to 30% of the time in the last 4 trials of extinction. And then a test, we're going to give them 4 trials of a tone alone and ask, are they freezing more or less than these last 4 trials of extinction? And we actually ran 2 experiments. We first ran 1 experiment, and after it succeeded, reviewers asked us to run another one, so we ran another one. The first experiment was a reinstatement experiment where we just, we gave a reminder shock and then tested whether they're freezing more. And the second experiment was spontaneous recovery. So we waited 30 days and then tested to see if they freeze more. And here are the results. So it worked. Basically, if we look at reinstatement is usually very effective, as you saw in the one of the first slides. So animals after reinstatement freeze 40% more than they froze at the end of extinction. That's with standard extinction, but not with gradual extinction. They're not increasing their freezing. I mean, this is numerically increasing, but it's not significantly different from 0. They're not increasing substantially their freezing even after getting that reminder shock. And reverse looks like standard. And the same for our spontaneous recovery experiment. So testing 30 days later, animals in standard extinction froze 10% more than they did at the end. 10% might not seem like a lot, but this is significant, and spontaneous recovery is a lot weaker than reinstatement in general. But for our gradual extinction group, no spontaneous recovery. They're freezing, if anything, less, but again, this is not significantly different from 0. So seems like they're freezing the same as they did at the very end of extinction. And again, gradual reverse looks like standard. So the idea is basically, if you want to think about kind of how to change a memory, we think a lot about learning in terms of prediction errors. Like if you see exactly what you predicted, you're not going to learn anything new. You learn from mistakes. You learn from making an error, from getting something unexpected. So if the prediction error is really, really small, you saw you saw exactly what you predicted, you're not going to have a lot of learning. And the larger the prediction error, the more learning you will get, up to some point where this is like so unpredictable, so different, that you're going to just create a new latent cause. And then you learn for that new latent cause, but we're looking here at how much you update the original learning. So the original learning will be reduced. The larger the prediction error, the more likely you infer a new latent cause and apply the learning to that rather than to the old latent cause. So there seems to be kind of like a sweet spot of like things need to be different enough for learning, but not too different that you would decide that this is just, a different ball game. So that's basically it. So I think about this, about learning in the brain, as we have mechanisms that I didn't talk about so much today, mechanisms of reinforcement learning, of learning from prediction errors that have been associated with the basal ganglia, with the striatum, with dopamine in the basal ganglia. And those are relatively simple learning algorithms or learning mechanisms. They're much simpler than what people talk about with deep learning these days. I would call that shallow learning. But I think that shallow learning really relies on these deep representations, on like taking, and this is a lot of our cortical real estate, a lot of the cortex, and some subcortical areas, but mostly hippocampus, frontoparietal cortex, orbitofrontal cortex. There are many areas that we've associated in other experiments with this process of clustering together different stimuli and kind of representing them in a way that says, all of these are the same. Learn about them with this easy, simple, shallow learning that you have. So shallow learning kind of relies on these deep representations that are very thoughtful. And just before I answer any questions that you have, I just want to say, I'm teaching a course on animal learning, and I try at the end of each class to talk about how this is relevant to daily life. So I thought I'd bring that in here. And I think one thing that I've learned from this is that slow learning can be good. One question is like, do you want to change what you already knew? Like you have a bad habit, for instance. Do you want to change that habit? If you want to change something that you already have previously, you want to do that gradually. Like fast learning, it looks like you've made so much progress, but actually you've just learned a different association. Like you haven't changed that old habit at all, and it will come back. It definitely, like habits really tend to come back. So sometimes I use this, with my kids, with myself, thinking that, slow progress is actually deeper progress in some sense, and I shouldn't be discouraged when things change only slowly. And the other thing that I take from this, and that you can take from this to your learning and your memory and studying for exams, etc., is that context is a really good signal for latent cause. Like we tend to infer that when we're at work or at school, that's one context, it's one latent cause. When we're at home, that's a different latent cause. The rules of the game are very different at home and at school. So it's interesting to think of that, of how like that determines boundaries of generalization and how we recall memories and things of that sort. Like if you want to differentiate memories, if you want to remember something distinctly, you might want to study that in a different context than you usually do. And I think that's maybe why when we're traveling, like we remember everything and time seems to move so slowly. It's like a completely different context. So it's not, it's creating all these new latent causes. And vice versa, like if you want to recall something that happened in some context, like for instance, you're taking an exam, like better to take it in the context where you studied the material. You'll be more likely to recall better. So that's it. Thank you for listening, and I'm happy to answer any questions.
I have, I think, two quick questions. I'll ask just one, I think. So, like context is often comes in like hierarchies. So my question is, I guess, like, have you explored how these kind of like hierarchies play a role in learning? If like you kind of recreate Sam's experiment, but now there's like maybe a hierarchical generative process, does it make it a lot harder to update those memories, a lot easier?
I think that's a super great question. I'm really interested in that, and I haven't figured out. I mean, true story. I had a postdoc in the lab. She's left now and has her lab at University of Oregon. We probably for a year tried to figure out experiments that would tackle that question. Like she would come with an idea and we'd be like, no, there's an alternative explanation, and try it again and try again. In the end, we we ended up doing other experiments. But it's a really good question that I'm really interested in, of like how like we have a hierarchy of memories, even like a hierarchy of resolution. Like if you think about, how was this semester? You're not like going in your mind, like fast forward through everything that happened this semester to tell me how was this semester. You have some kind of global memory of how is this semester. But I can also ask you, how was the week of elections for you, or how was the first week of the semester? And you can go back to that specific thing and tell me something at a better resolution. So I think I'm thinking like in this model where you're saying, okay, like you put something in memory. You don't put something in memory in one place. You put it in several places. In the like high order there, it's going to just contribute a little bit to the overall impression. And then in other levels, and do we determine these levels in advance? Can we change them later on? I mean, I'm not a memory researcher, but I've gotten more and more interested in memory, and I wish I could have some kind of like Golgi stain that would stain memories so I could see their structure, because I'm dying to know how they're organized. And we're trying to use fMRI and decoding of different events to get at this. But as I said, like we still don't have a good experiment. But super question.
Thanks. Yeah, that's a good answer.
I had a question, but Neil had a question in the chat.
Yeah, I see his question. So how do you learn to generalize from the psychologist's office to the real world? So that's a really good question. Not last year, but the year before that, I was on sabbatical and I decided to learn CBT, cognitive behavioral therapy, because a lot of our research now is applying these models to, like, it's not a coincidence I talked about PTSD. It's applying these kinds of ideas to mental illness and seeing if we can, make a dent there in the understanding of mental illness. And in cognitive behavioral therapy, one of the things that you do is you indeed gradually, you learn a skill in the psychologist's office, and then you do it outside. Like, if someone has a phobia, a fear of elevators, we talk about it, but then we go to the elevator, then we go to the elevator in their building, and you literally you take it out and try to generalize as much as possible. You give them homework, do this in many different places. So it's, through gradual learning and approximating more and more real life and not just the clinic.
My question was a lot similar to that one. I wanted to ask about how memory traces and clustering can be translated to treatment of PTSD. And in specific, I know with trauma, you have to deal with the patient not even having memory of the actual trauma in the first place. I guess it has to do with the amygdala and hippocampus interacting at that moment.
Mm-hmm.
So how do you tap into the lack of that memory in the first place with this, if that makes sense?
Mm-hmm. So I can say two things here. One is, I kept giving the example of PTSD, but I think gradual extinction, for instance, as a method is more applicable. So, right. So for the rats, we can bring them in and, give them a shock, and they have no choice, right? But a patient coming for treatment, if the first thing you do is you scare the hell out of them, they're not coming back, right? That's not going to be a widely popular treatment method. So I think this kind of gradual process might be more applicable to things like, for instance, recovery from addiction, where, again, like going cold turkey, abstinence, it's not even extinction. It's really like abstinence is you don't have the stimulus or the outcome. You don't have either of them. And we know that animals don't forget associations, neither do people. So abstinence seems to me like almost the worst way to try to solve addiction. And indeed, there's the rate of relapse is huge. And more gradual reduction, nicotine patches, etc., might be more like gradual extinction and might be more effective. So that's one side, an answer to a question that you did not ask. The question that you did ask is, what do people do with PTSD? So I'm not a clinician, and I can't tell you the whole gamut of different treatments, but I know what is done in CBT and cognitive behavioral therapy. And there, one of the leading methods that really works quite well is called prolonged exposure. And the idea is you ask the client to tell the story of their trauma, of their traumatic event. And there's a really interesting issue about generalization there, because if they've had more than one, they can choose one event, and it somehow, if it helps all the others as well. You could just focus on one. So they take one traumatic event, maybe the worst, and they tell the story of that event in first person present. So not then I did that and then that happened, but like, and now I'm seeing, this person coming close to me and they have a knife and, they're threatening me. And the therapist tries to make it as close to the true story as possible, to the original memory as possible, by really eliciting, and what are you smelling and what are you feeling, and all of like the whole sensory experience, but also making sure that they know that they're safe and reminding them, you're in the office here with me, you're safe. So it's a very delicate issue of trying to get the person to go, basically to get that shock again, but not totally freak out, not have a panic attack. And that story is recorded, and then they're asked to listen to it every day of the week. And then they come back the next week and they tell the story again, and it's recorded, and they listen to it every day. And this continues for 6 or 8 weeks. And it's really effective in two things. One is over time, and you started by asking, what if people don't have a precise memory? Their memory becomes more and more precise. So they find out more things that they thought they didn't remember or didn't know. I mean, we don't know what the precise event was, but they recall more and more details that make the story make more sense. And in some sense, there's this whole other story that's not about gradual extinction, that is the idea that a traumatic memory, so our memories in general, you can think of them like, books on a bookshelf, right? You can go and open a book and look in it, but you can also put it aside, like you can put it back. It's not like our memories are flooding us all the time, but traumatic memories, they do flood. And the person who taught me, who taught this course that I took, she said, it's like the traumatic memory is like, instead of being a book in like, or a binder on the shelf, it's like all these pages strewn on the floor. And every time you go to any memory, like you see them and like you pick up a page and you immediately like, it's a very fearful memory. So you don't want to read the rest. So you like throw it down and like, there's this mess. And so this telling of the story is like, it lets the client really kind of organize this, put it in a binder, put it on the shelf. But the other thing that it does is really gradual extinction, because over time, they have less of an autonomous response. Like in the beginning, they're very, very, like it's really horrible. They're crying, they're sweating, they're like the whole panic response. And over time, they're just telling it. It's just a story. Like they're able to distance themselves from it, of like, yes, this happened. It doesn't define me. And I know it's not dangerous to think about it. I know it's not dangerous to talk about it. I've done this many times already, and I see that it's fine. And they're able to put it aside and really kind of resume their life. And so I think there is a kind of gradual extinction story there as well. It's a really cool method. It was developed by Edna Foa, who is a psychologist at UPenn, so close by. You should have her come talk to your group.
That's really interesting. Thank you.
All right, guys. So we have time for one more question. So if anyone has like a question that they really want to get out, go ahead. And if not,
I was actually wondering, you were saying about the causes, and I was really confused in the beginning. Is it the same thing as in just one memory a part of a set? Because I felt kind of that a cause would be extrapolating level up, like mice would have to infer something like instantly in my head it was, oh, like a god causes it, like I don't know, but that's probably wasn't what you were trying to say. More was like a kind of a part of a set.
Yeah, so it's interesting that you say God, because I think, you know, God is the ultimate latent cause. We can't actually see that cause, but I think it's more that I'm thinking that the way we or rats group experiences is we think all these things are the same. The fact that all these things are the same is because kind of they were caused by the same generative mechanism, you know, like all these meals were cooked by the same person, or they were eaten, they were, you know, in the same restaurant, like there's something tying them together. And so you can call that the cause. The cause is, this is like all the food that I eat at Nomad Pizza. So you can think of the latent cause as literally the chef in the other room, so I don't see them, but you can also think of it as just the fact that all of these come from the same source, all of these like observations, and that source might be observable, might not be observable. So I'm calling it latent cause, but sometimes the causes are not latent, sometimes they're observable. It's just a grouping of things that are of the same kind because they come from the same thing in some sense. Does that make sense?
Yeah.
Well, thank you very much. This was fun. I applaud the fact that you can do science at these late hours. I guess I was once younger and could do that too. I'm joking. I'm usually up till midnight trying to catch up with my email ineffectively. Yeah. I'm still impressed that you all stayed awake, because it's kind of hard to listen to a talk at this late hour. So thank you so much, and thanks for the questions. And this was really fun.
thank you very, very much. Really appreciate you having.
And you know, there's one thing that I
me,
totally should have said and didn't. So we have the Rutgers-Princeton Center for Computational Cognitive Neuropsychiatry, CCNP. So it's Princeton. It's ccnp.princeton.edu is the website. And that is a joint center with Rutgers. Some of the Rutgers people are at this center, and it's the center is two things. One is it's literally like physically a place where we run studies, cognitive psychology, cognitive neuroscience studies on patients. But it's also a seminar series. So we have seminars every other week on Wednesdays at 10 to 11. They are now all on Zoom. They're normally all at Rutgers and the Piscataway campus. But now they're of course on Zoom. So if you want to listen in to those, then on our website, ccnp.princeton.edu, there is the email of Ed Clayton, who you can email and get on the mailing list, and then you'll get the abstracts of the talks. And if you want, and the Zoom link, and if you want to, you can join. There are pretty cool talks there. Some of them are about computational modeling, some of them are psychiatry, some of them are psychology, cognitive science, and it's all, and some of them combine. It's a whole group of people who are trying to think about these kinds of models and experiments in light of or in the service of understanding mental illness.
Yeah, that's super interesting. I just posted the the link in the chat
Yes,
if any of you guys want to check it out.
exactly. Yes,
Um,
and I'm co-director of that center, so full disclosure, I'm promoting my own thing. But it is a nice group of people that we have there. So if it interests you, please do join.
Awesome. Well, I mean,
Great.
I think it goes without saying. Thank you so much. We had a lot of fun. I wanted to address also the comment you said earlier. Just listening to a scientific talk, honestly, it didn't feel like one. I think because it was so easy to apply it to real life, right, and to understand. Even though it's about animal learning and memory, I think it's so easy for us to apply it to our own lives. So I think it was kind of like an insight into a bit of ourselves, right? And so yeah, I think it was really interesting. And again, we all appreciate you coming here, even though you have such a busy schedule.
Thank you. And I apologize to all the people that I did not answer their emails, even at 1 a.m. when I was trying to catch up with emails. It's just a lost cause at this point.
Okay, well, before
Good
everyone
night.
leaves, yeah, I want to say good night to you, Dr.
I'm
Niv.
going to leave. Yeah.
Okay, yeah, go for it. Thank you so much again. Before everyone leaves, I want to remind everyone that we have an interest form. So if you want to just put down your email and like your name, your major, your graduating year, all that stuff, so you can be up to date on the emails. And share it with anyone else who you know is interested in the meetings but doesn't get any notifications. And share the Discord with them too, the Discord invite. But yeah, that's pretty much it for the meeting. I'm glad you guys came. Thank you very much, and we'll see you next week. Bye, guys.
Hi, everyone.
Guys.
Bye.